This is a paper titled Pi-to-Pi Orbital Transitions and Photo-degeneracy in C.acuminata dye solar cells. C.acuminata is actually the scientific name for Kola nut. Kola nut exists in about 125 species, but the reason for our research is C.acuminata has the highest economic importance. The paper was written by the following people, and we're all from different walks of life and located in different places. Dye solar cells have actually acquired a huge prominence since 1991 that they were first discovered by Grutzel. And the reason is that silicon solar cells are quite expensive. As opposed to dye solar cells, they are available all year round and they're cheap. They are also easy to fabricate following very simple procedures. Aside from that, they have some adjustable optical properties like the transparency, the color. They are also able to work under conditions of low lighting, which does not happen in silicon solar cells. And as such, they are available and they are prospective candidates for future research. I'll be introducing some key terms. Dye-sensitized solar cells. They are actually photovoltaic devices that are able to convert solar energy directly to electricity. And I'm sure you agree with me that all technologies in the world are driven by electricity. And that is important for this generation, especially when we talk of global warming, when we talk of the fact that we have limited resources to fulfill our very unlimited wants. So today we're going to be talking about C.acuminata dye. I'm going to be telling you about how the dye is obtained, but obviously we're going to be ending with the photoelectric properties. We're going to also discuss some of the surface morphological characteristics using the scanning electron microscope. So the key terms, I continue with the titanium oxide. That's the photo oxide on which we're going to base the dye. The organic dyes, they are several. The introduction will incorporate some of that. Then photo-degeneracy, the idea is these dyes do not last forever. They decompose over time. So I'm going to be showing you some formula as to how the degeneracy can be calculated. By the way, I am Temitope Aboduri. So I'll go on with my presentation. Now, every dye-sensitized solar cell has basically these components. It is like a sandwich, and inside the sandwich, you have the electrolyte. Aside from the electrolyte, you have the photoanode. That's the framework on which the dye is put. In between, you have the transparent conducting oxide. In this experiment, we have used the indium doped tin oxide. So you have the platinum coating the counter electrode. So you can just appreciate this. You can see the sun impinging on the dye solar cell, and when it impinges, it liberates an electron. Thank you. Now, there are some important chemical reactions that have to occur. The first is that when the light impinges, it causes a transition of electrons. Now, electrons normally occupy the layer called the pi. Okay, so now depending on the energy or the frequency of radiation, several transitions can occur, but the most probable normally is from pi to pi star. Okay, aside from the pi to pi star, you can also have from pi to the sigma star. You can also have from pi to the unhabitable orbital shells. But we'll be focusing on the most probable, which is from pi to the pi star. So let's look at these equations. You have the electron, the CB is the conducting band, where you have most of the electrons until the solar energy impinges and energizes these electrons, okay? When it does that, the dye is just in the ground or the highest occupied molar orbital. So this is what happens in the equation. The dye becomes liberated and it goes on, and then you have the conducting band. Where's the conducting band? Now we're looking at the photoanode of the titanium oxide. That's the first equation. Then the second equation has to do with the electrolyte, which must obviously be a redox mediator. That is able to reverse And when it reverses, it's able to recover exactly to its original state. You have the iodide, the mediator, the electrolyte there. It is going to acquire that electron and see what happens there. It is reduced. But the beauty, as I said earlier, is it's able to recover and reverse to its normal state. Then you have the delta H. That has to do with the transition. The transition has to do with the energy difference between the different band, the energy bands, okay? You have the LUMO, that's the lowest unoccupied molecular orbiter. And the difference between the energy in the highest occupied molecular orbiter, that's what gives us the delta H. And this is just introducing my terms. E has to do with the electron in the conducting band. D is the dye. I is the redox electrolyte. My materials and method. The C.acuminata dye was obtained from the leaves. They were harvested, and when they were harvested, they were dried in a condition that is just devoid of direct sunlight, so as not to tamper with the chromophores. When they were just dry and they assumed constant weight, the leaves were weighed and milled. After milling, they were spread out to dry so that they would not be subject to bacterial growth. So they were soaked in methanol, because methanol would offer a kind of situation where in some experiments they talk about ethanol, but methanol was chosen because it's actually friendly, research friendly. And then the dye solar cells were fabricated using the ductile blade method, which was purchased from the Solaronics, and attention was paid to the quality of materials. The counter anode was coated with platinum, just from a naked Bunsen flame. As much as possible, the materials used were easy to get and environmental friendly. The titanium oxide was fabricated, after being fabricated using the sintering method. The oven was set to about 450 degrees Celsius after applying the ductile blade method. The area, the active area was just about 25 millimeters by 4.5 millimeters of the ITO. And then the dye was only grown after the dye solar cell was fabricated and allowed to cool for some time. My method is just shown. Okay. So according to Ohm's law, the current is proportional to the potential difference, provided the external conditions are constant. Now, the current is relatively, of course, is a function of the insolation, and the potential difference was obtained using a Voltcraft digital multimeter. And then there was a variable load, which we changed. And when the load was changed, the potential difference also altered. And the different characteristics is what we got as the IV curve, which will be shown later. Okay, the results. For different electrolytes, there were 4 in all. The potassium chloride electrolyte was used. The potassium bromide was used. The potassium iodide was used. And the mercury chloride was also used. For these different electrolytes, we obtained different results, but under the same condition of insolation. The best result was produced by potassium chloride. The short circuit current obtained was 1.666, and it was recurring, approximately 1.7 milliamperes. For the open circuit voltage, the best was also given by potassium chloride. The value was 101.4 volts. The efficiency which we're concerned about, the best was given by potassium chloride. We had 0.56%. The worst electrolyte, when we fabricated the dye solar cell, was given by potassium bromide. The short circuit value was 0.1 milliamperes. The efficiency was given by 0.018. That was the least here. And the explanation is that the chloride ions were favorably discharged. They were able to form better covalent bonding with the titanium oxide framework. The potassium bromide in these solar cells was not favorable. Obviously, it led to some trap sites and recombination occurred, which led to unnecessary heat and poor efficiency. My discussions. When we compared the efficiency obtained in potassium chloride to the potassium bromide, we were able to get about 20% more from the potassium chloride. And I explained that already. It had to do with the favorable reaction being disposed to the chloride. And when we look at the fill factor, which describes the quality of the dye-sensitized solar cell, we were able to see that even though the fill factor of potassium chloride dye-sensitized solar cell was less, the efficiency was higher. And the factor attributable for this could only be that probably the leaking electrolyte was what resulted in high internal resistance. And as I said earlier, it wore off in the potassium bromide, leading to the poor efficiency in potassium bromide. And the quality of potassium chloride can be attributed to the leaking electrolyte. So subsequent researchers will take note of this. This is the UV of the C.acuminata dye. When we look at the diagram of the UV, it tells us the absorbance peak of the dye. The absorbance peak is close to from 400 to 700, that is the visible range. That's about 380 nanometers wavelength. And what it means is that C.acuminata dye the color it will feature in is close to violet. It's darkish. Now, what is the implication of this? Let's look at the absorbance index. That's about 4.0 absorbance index. What it means is this dye is actively absorbing in the visible region of light. When we see between 200 and 300, we see a spate of reactions there. And that has to do with sporadic transmissions before it stabilizes at 318 nanometers. So the UV tells us normally that it tells us what happens from the excited state, from the ground state to the next state. So this gives a summary of the pi to pi star absorption. Okay, the SEM results illustrates some wavelength peaks. Okay, the scanning electron microscope is actually able to give us an in-depth. What happens? It tells us a story of what happens at nano depths under the layers. Okay, and we'll see that it reveals wavelength peaks and highest absorbance occurs in the ultraviolet region, which means that aside from what happens in the UV section, at 650 to 660 nanometers, absorption also occurs, and it's also collaborating with the UV. It's in the blue region of the electromagnetic spectrum. Let's go on. Okay, this is the FTIR. This is the reverse of what happens in the UV spectroscopy. And this tells us what happens from the excited to the ground states. Okay, we're going to be seeing that there are about 20 different peaks showing the functional groups of the C.acuminata dye. It has the iodoalkanes, but interesting to note is the secondary amines, which has 84.135 intensity. And that also tells us something about the preferential discharge. Okay. We'll just conclude with the fact that the efficiency of the dye was calculated using a very simple formula where we looked at the change in absorbance over the original absorbance expressed in percentage. And we got a value of 0.6, and it was under actually very low sunlight conditions. So if the conditions were favorable, the chances that the efficiency would actually be higher. And as a result of this, C.acuminata dye is considered a prospective candidate for commercialization of dye-sensitized solar modules. Why? Because in a prior literature, Greta was able to say that if the whole world was covered with dye-sensitized cells of 0.1% and 10% of the world was covered, we will have enough energy to be able to satisfy our needs for 1 year. And with this, I will go to the references. Thank you very much.